We can expand our ability to integrate and differentiate if we look at the inverse trigonometric functions. The inverse trigonometric functions emerge as follows. Suppose y is some trigonometric function of x. The inverse trigonometric function, y equals inverse trigonometric function of x, satisfies the relationship x equals the trigonometric function of y. But unless we're careful, this is not going to be a function. And the reason is that the trigonometric functions are periodic. So, for example, suppose I want to find 3 solutions to the inverse sine of 0 equals y. By definition, if the inverse sine of 0 is equal to y, then 0 is equal to the sine of y. And so let's try and find solutions. If y is equal to 0, then sine of 0 is 0, so y equals 0 is a solution. We can find another solution. If y equals 2 pi, then sine of 2 pi is 0. And if y equals negative pi, sine of negative pi is also equal to 0. So y equals 0, 2 pi, and negative pi are 3 different solutions. And in fact, there are many more. And so because the inverse sine of x equals y will have many values of y for any given x, the inverse sine of x will not be a function of x unless we identify which of these many values it returns. We sometimes say we must choose a branch of the inverse relation. This isn't actually a new idea. You've already seen this before in the context of square roots. If y squared equals x, we say that y is a square root of x. So 5 and negative 5 are both square roots of 25, since 5 squared is 25 and negative 5 squared is 25. But in order for square root of x, this algebraic symbol, to be a function, we need to choose a branch. Which of these square roots is this thing, square root of x, going to give us? And so for y equals square root of x, we choose the positive number that satisfies y squared equals x. And so if I write square root of 25, this can only be equal to 5. So let's consider those branches for arcsine of x. Suppose sine of y equals x. We want to find y equals arcsine x as a function. So we might begin as follows. We know that x has to be between negative 1 and 1. So we want to limit y to an interval that, first of all, includes a solution to sine y equals x for x between negative 1 and 1, and also that if a solution exists, only one solution is in that interval. So let's consider a few intervals and see which one will work for us. So for example, how about 0 less than or equal to y less than or equal to pi? Will this work as an interval? And unfortunately this won't. This won't allow us to solve sine y equals negative 1. There's no solution in that interval to this equation. Well, how about y between 0 and 2 pi? While this meets that first requirement that we include all solution to sine y equals x for x between negative 1 and 1, it misses the second requirement that only one solution is in the interval. There are multiple solutions to things like sine y equals 0. So how about y between minus pi and pi? And we meet that first requirement that sine y equals x will have a solution, but again we fail that second requirement that there are multiple solutions to equations like sine of y equals 0. Well, third time's the charm, so if we don't find it by the third time, we should give up and join the circus. Okay, let's try one more time. How about y between minus pi over 2 and pi over 2? We see that this will include a solution to sine y equals x for any x between negative 1 and 1. Moreover, if a solution exists, only one solution can be found in this interval. And so this suggests the following definition for arcsine. We'll say that y is the arcsine of x, where y is between minus pi over 2 and pi over 2, and sine of y is equal to x. By a similar argument, if we want cosine of y to be x, we want to define y equals arc cosine of x as a function. And in this case, we'll choose the interval y is between 0 and pi. And likewise, if tan y equals x, then y equals the arctangent of x, where y once again falls between minus pi over 2 and pi over 2. One more note. The more important something is, the more names we typically have for it, because different groups of people find it important and they come up with their own names for it. So even though we use arc, cosine, arcsine, arctangent, an alternate set of notation is sine inverse for arcsine, cosine inverse for arccosine, and tangent inverse for arctangent. The notation for the inverse trigonometric functions is not consistent. So we're in calculus, and the first question that we always ask whenever we get presented with a shiny new function is, what's the derivative? So we might start with a definition. If y equals arcsine of x, then sine of y is equal to x. And so we can use implicit differentiation. Now, while I do get the answer derivative equals 1 over cosine y, since the function is in terms of x, its derivative should also be in terms of x. We don't want to leave our derivative in terms of y. So that means we need to do some algebra and or trigonometry. And one of the things we know is the Pythagorean identity, cosine squared y plus sine squared y equals 1. We can solve this equation for cosine y. Now remember, the square root gives us the positive number whose square is cosine y, but I have the possibility that there may be a negative number in there as well, so I do have to indicate plus or minus square root. And because I know that sine of y is equal to x, this radicand becomes 1 minus x squared. However, there's a problem. We can't use plus or minus in a function, as this would give us more than one output. We have to make a choice. So again, we'll go back to our definition of what arcsine is. And remember that if y is equal to arcsine of x, then we know that y is between minus pi over 2 and pi over 2. And this means that the cosine of y is going to be positive. And so that means while cosine of y could be plus or minus 1 over x squared, what it actually is the positive square root, which we can then substitute back into our derivative and get our form of the derivative of arcsine of x.